And I want to talk to you about some research that I carried out, that whilst John wasn't actually involved in it directly, he was a key enabler, both of the research itself, but also of me as an individual and my career development, because subsequent to this, I actually joined the firm working with David as the project manager for Pleiades, of all things. And what I want to do quickly is just kind of show you that it's one thing to be able to handle and manipulate image data, but actually whether that's really vision is quite another thing. Let me take you back to the 1980s. Remember that decade? Many of you do. CCTV was just really starting to be deployed, and we had a number of challenges. You've already seen one, which was this problem of phantom queues and queuing on motorways, but also things like turning movements at junctions were quite difficult to obtain, and often you were having to do quite difficult survey work. So CCTV was a great attraction because you've got a wide area view, you can see multiple lanes, you can watch traffic spatial behaviour, and it's quite easy for us to understand. We can integrate with it, we know what it's about. So there's also the potential for actually reading more and more information. But you also have to remember, we were still in the analog universe. CCTV, 512 by 512 picture elements, pixels, but actually that was being foolish. It was actually 2 times 256 lines, a quarter of a megabyte of data for each image. So something like 6 megabytes of data per second. Andy mentioned 386 computers. You try and get a 386 computer to do 6.25 megabytes of data per second, you're going to hit some problems. So we were just starting to see solid state sensors for the cameras themselves, but everything else was analog. Output was all via copper cable. Recording was all on videotape. Remember the days of videotape. So the technology we had available created some opportunities. My then supervisor and the investigator of the initial research I carried out, Dr. Lewis Wilson, who's here today, he was actually in a building alongside the Department of Physics, and they built a thing called the CLIP-4 parallel processor. Now, at that time, there was a kind of feeling that individual processors themselves were kind of getting towards the limit, so what we needed was a lot of processors all working together. And they built this array of just over 9,000 processors aligned in a square matrix that could process each picture element individually and in parallel. It was about the size of a wardrobe, and you had to have something about the size of a chest of drawers to control it. But at this time, the good old PCs were just starting to turn up on the desktop. So we had 80386, 25 megahertz, 4 megabytes of RAM, plus we needed some additional kit to actually grab the frames from the videotape, and then some specialist video boards that could handle the data. But the difference between these two is that 96 by 96 pixels is not very dense, and it means that it's very, very difficult to pick out objects at any distance. And if you do some fairly basic geometry, you find out it's something between 50 and 90 meters. It's really not that useful, particularly when you're trying to look down a motorway. The IBM AT solution could actually look a lot further, but it was a lot slower. So we had to think around that. And just because we keep comparing things to mobile phones, in my pocket is this mobile phone. And basically you can see that everything that was a K or an M is now an M or a G. It has parallel processing. It can record 3 hours of high resolution video in my pocket with a battery that lasts for 24 hours. So things have moved on hugely. And to give it some kind of scale, this represents an exponential growth of doubling about every 3 to 4 years. So here's some actually the research outcomes we achieved. We did manage to track vehicles round a very limited junction. And you can see here we've got 3 different vehicles that we were able to identify using the CLIP parallel processor. But we could see that this was quite difficult. It was quite difficult to segment out individual vehicles as they enter the junction. With the IBM AT system, which we gave the acronym INCAPAX to, we actually developed a system that could see those phantom queues on the motorway, shown in red here. And we were actually able to get together and look at a lot of data. And Wootton Jeffries were instrumental in gathering this data for us. Andy Graham, Keith Keane, Dave Kelly all worked with me at John's behest to gather a whole range of different videotapes that we could use. One thing we did discover, though, was when you go out to record congestion, it disappears. So maybe we should do more recording. Oops. So, the other thing we have to think about is it's not just about the sensor, it's about the system. And this is a very early system diagram from a project that was funded through the European Union. Again, this was John supporting collaboration, international collaboration. We had half a dozen companies involved with this from Spain, from Belgium, from France. We had several people promoting different computer vision image processing solutions, and we had a whole system that could take this disparate data and create an output that can be used by the traffic controllers. So we were actually really moving things forward. I think one of the more interesting things about this is it actually did get to be shown on Tomorrow's World. I didn't appear, but the system did, although I'm crouched behind a desk, desperately waiting for a cue to press the button at the right time. So, where have we got to today? Well, CCTV image processing is widely used. ANPR is now pretty well ubiquitous. It's everywhere. If you drove here today, even if you drove to the station, you will have had your number plate read multiple times. Queue detection is being done, but generally in things like tunnels. We are seeing individual vehicle control, junction control, and there is pedestrian and cycle detection. But these are all quite constrained things. They use specialist hardware. They've got rid of a lot of the externalities to do with lighting conditions. But we're now at this kind of developing stage where we're actually seeing some really interesting things, where we're actually able to start bringing in the context of vision that I think is actually going to be helpful in turning things that are great most of the time, but some of the time they actually fail to operate. And a lot of the time, they're not providing that certainty of outcome that we can use for control and for true operations. So I want to hand over now, but before I go, I just want to say that as I move on to fade off in my career, I have more time for reflection. And one of the things that I can reflect about is that I developed something that's been on the end of Maggie Philbin's finger. So now I'd like to invite Nicolette to come up and give us some really interesting stuff about what's happening today.
Good evening. Today we are here. So Dr. Hoose has taken us through the journey of computer vision, and I'm here to ask a simple question. How will that CCTV analytics transform road safety? So as we know, every day, thousands of hours are being recorded from our road network, but most of it, we don't really see it. So the current CCTV system is the eyes on our road network. It is trustworthy, it is operationally robust, and it comes with a lot of opportunities. And it's mostly there to support traffic and incident response. The infrastructure is predominantly pan, tilt, zoom cameras, and they are designed primarily for operational monitoring. And the resolution of these cameras is aligned with the original requirements when they were implemented on the road network. And they also go through multiple analog to digital conversions, which can introduce latency. So how can we actually watch this video and understand the data from this video? Let me show you a few examples that we do at National Highways. Stopped vehicle detection is the most safety critical challenge on the motorway. What you are seeing here is automation supporting the operator in order to identify the vehicle, in order to get a quicker response time, because this can help save lives. Here you're seeing two different types of cameras where we can actually identify the stopped vehicles. So the automation is helping the operator. It is not replacing the human. It is actually giving back time where seconds are really important. Another example is this slide. So maybe it is more subtle, but arguably more powerful. This is because this is a near miss. It is not a collision. It is not incident reporting, but it does not even show in our data, unfortunately. So what we're doing here is we're using trajectories to identify whether the vehicles, if they continued on that same journey, a collision would have happened, which is represented by the time to collision in the bottom picture, which is 835 seconds, which is less than 1 second, should they continued on that same journey. So this is very valuable for safety. Another example